All right, I feel like I had to sign into Zoom 5 times for it to actually commit to me. It was weird. All right, so welcome back, class. Good afternoon, all that stuff. Hope we had a good weekend. We're going to pick up where we left off in 5.6. As a reminder, your homework, I think for 5.5 is due on Wednesday the 30th. 5.6 will finish today, so I have that due date set up as a week from today, which is October the 5th, I believe. Yes, October 5th. And then we have 2 more sections to cover after that. One of which, in 5.7, you may have seen referenced back in 5.2 for maybe one problem. It's either 1 or 2 homework problems. And yeah, so I don't want to get into that yet, but the idea of an inverse trig function. But for now, leaving off where we had in 5.6. So 5.5 was sine and cosine graphs, the waves, the more traditional waves, like the blue thing you see right here. That's a sine wave. Or this, or the blue one you see here is a cosine wave, but shifted 90 degrees to the left, because normally you start here and then keep going until you hit 1 again at 2 pi. We said that whenever we want to graph the reciprocal functions of sine and cosine, what we do is we draw the sine or cosine wave, and then we just draw parabola-looking shapes from those, but they'll be sandwiched between 2 asymptotes, and the asymptotes are wherever the original function was 0, because the inverse trigs mean you're taking a reciprocal of 0. 1 divided by 0 is undefined. So that was why these cosecant and secant graphs have all these asymptotes, because sines and cosines have all those zeros, which means flipping them means a bunch of asymptotes, a bunch of undefined values. So we did the graph of cosecant by flipping sine. We did the graph of secant when I say flipping, I mean metaphorically speaking, I suppose, by flipping the cosine. But we said that because it would look really ugly, if I had originally taken this thing up to 2 pi, so there's 2 pi, that means that the secant graph would have looked like this. You'd be cutting off this part right here. You'd be completely ignoring all of that section, and you would have this, I'm drawing what you'd see in red, and then this, which looks like 3 different pieces, which is why we don't do it that way. We just said, hey, let's just draw it from negative pi over 2 to 3 pi over 2 instead. That's still 1 period. That's still 360 degrees worth of x values there. But then you only have just 2 looking parabolas, 1 up, 1 down. We didn't have to worry about the sliding around with this one because they naturally happen, and put the asymptotes in good places. Then we did the tangent and cotangent. The first thing we had to make special note of is that tangent and cotangent have a period of pi over b, or pi if there's no other modifiers there, whereas everything else was 2 pi or 2 pi over b. They have the same asymptotes because tangent has a cosine in the bottom, so where we're cosine 0, which are the multiples of pi over 2 and adding pi, you'll have your asymptotes. And then cotangent has sine in the bottom, and wherever sine is 0, this will have asymptotes which are literally just at multiples of pi. So we had all those great details in there. And we said that these graphs end up looking like cubics sandwiched between asymptotes. And the tangent had the same issue as the secant graph, where if you went from 0 to pi, you'd have half of it going up and then half of it going down, separated by an asymptote, and it would just look weird. So he said, so we can make it one graph-looking thing in one waveform. Let's just sandwich it between 2 asymptotes here and here. Then cotangent didn't have that issue. You were able just to go from 0 to pi. It's funny how some have the issue and some don't. And it always seems like one in each of the families has an issue and the other doesn't. And then we graphed 2 tangent of 6x. And you can see all the work. I'm not going to reiterate that. Look at last lecture for that detailed work, because now we're going to go straight into example 2. It'll be to graph y equals the secant of 2x. Still a good idea to identify your a's, b's, and c's like I did last time. So for this, There is no a written, so it has to be 1. There is a value in front of the x. Sorry, I'm looking at x, so I was about to write it, and that's a 2. There is no plus or minus number, so there is no c, which means there'll be no shift. Your c is 0. I'm just trying to keep things organized in the same way. Okay, good. So therefore, our amplitude, and again, I put it in air quotes. I say air quotes, but I'm not doing this in front of you. I put it in quotations because it's not a true idea of an amplitude. It's not a peak, but it at least does give us an idea of something. So that's related to the a, which is not the 2, that's the 1. Then the period should be the pi over b, which in this instance is going to be 2 pi. I said pi, didn't I? I meant to say 2 pi. This is secant, so 2 pi over the b, which was 2, making it pi. I had the answer in my head, which is why I said pi initially. And then there was no shift. All right. The only thing we have left to figure out is what we're going to add over and over and over. So where we take the period, which is pi, and divide it by 4. And there's no reduction to do there nicely. Now I say add, and then in the problem for the tangent, we also had to subtract. So I just like to make a little memo that maybe you have to subtract it as well. So a secant graph, that was flipping the cosine, right? So secant graph, that was flipping the cosine. So here was the cosine wave, and that was one that we did have to shift over a little bit, that kind of annoying negative pi over 2 aspect. So you would have had to have accounted for that as well here. But you don't just start it at negative pi over 2. You're going to have that issue where you've got to add and subtract the pi over 4. So that number is not going to just be pi over 2, negative pi over 2, that is to say. This pi over 4 dictates it. So I say maybe subtract, but you are definitely for this problem. I just don't want to leave that permanently up there. All right, so our second point, that's going to be 0. Our second point is going to be 0. Notice I didn't start at the first one. I started with the second one. And that's, again, I'm going to scroll back up to the reasoning. Oops, too far. There it is. This is the type of graph we're going to make. We're graphing a secant, a variation of a secant of 2x. So we can't just start at 0. We have to subtract once to get the left point. Then we'll go back to 0 and add 1, 2, 3 times to get the other points. It's a very weird setup, I know. So the first point would be the previous one, 0, but then we're going to subtract that adding number, which is pi over 4, which would give us negative pi over 4. Then the third x value, we take the second one, 0, because if you take the first one and add pi over 4, you'll get to the second. And then we add the pi over 4, which will give us pi over 4. The fourth point, we take the previous one, which is pi over 4. Whew. I was trying to get to the mute button for that, sorry, excuse me. Oh man, give me about 15 seconds, I need to go get a tissue. All right, I'm back. All right, so that just looked a little, no, I hit erase. Erase for the third time. I'm just making that pi a little prettier. So we take that original, the third point, and we add the adding number of the pi over 4, which pi, 1 plus 1 is 2, that's 2 pi over 4, which reduces to pi over 2, of course. And then finally, our fifth point would be the previous one of pi over 2, but I'm going to use the non-reduced version. We talked about that last time, how it's just better to go and do that, otherwise you're going to get the LCD anyways. So 2 pi over 4, then add the adding number, pi over 4, and then it'll give you 3 pi over 4. Now, if you remember that little trick I gave you, it said that if you took the first point, which was the negative pi over 4, if you added the period of pi, which is 4 pi over 4, negative 1 plus 4 is 3, you do get the fifth point. So everything lines up perfectly. Again, if you think you're supposed to start at 0 and then go to pi, I mean, you'll have 5 accurate points of the graph, but it will not be the waveform that I would want. Now, again, in my math lab homework, that's not an issue. In the test, because I'm going to be doing that in my math lab, it's not actually an issue. I have said that I might ask you to do by hand, you know, all of this detailed stuff for me to see and then just draw up the one waveform. I will be honest, I'm not going to have you do it with the secant, cosecant, tangents, or cotangents. For the secant, cosecant, tangent, or cotangent, if I throw one on the test, it will be like in my math lab homeworks. And that's because we're not going to be using this as much throughout the semester, whereas the sines and cosines we will circle back to, pun intended. All right, so we can start drawing our table of values in a better way than that, please. So x, y, all we've got so far are the x values of negative pi over 4, 0, pi over 4, pi over 2, and 3 pi over 4. And the y values we're supposed to get by doing all that flipping and stuff. Now, you can go straight to these if you remember that the first and the fifth are supposed to be the undefined. So we can say, hey, what's that secant graph look like? Yeah, the first, the third, and the fifth are supposed to be undefined because the cosine graph had zeros at the first, the third, and the fifth when it was adjusted to make it look more like a sine wave. Again, that's weird feature 1. So it's undefined on the first, third, and fifth. You can do the work to confirm that if you like, but I'm not going to do it this time. If you plug those in, you will end up getting undefined answers. I'll show it for the first one first. So that was the secant of 2 times negative pi over 4, which is the secant of pi over 4, which would be 1 over cosine of negative pi over 4, by the way. That is a negative still. So 1 over cosine of negative pi over 4. Well, cosine of pi over 4 is square root of 2, hold on, pi over 4. Four? No, 2. What? I knew something looked wrong. I keep looking at the pi over 4s over here. 2 and the 4 reduced to a 2. There we go. So that's the secant of negative pi over 2, which would be 1 over the cosine of negative pi over 2. When I wasn't going to quadrantals, that was my red flag. It's like, no, they should only be quadrantals. So cosine of negative pi over 2. I didn't pull up my cheat sheet. Remember, this is stuff you're supposed to know. But at negative pi over 2, we're down here. The x value is 0. Cosine takes the x value. So that's 1 over 0, which is undefined. Third and the fifth will follow suit. If you don't trust that the second one is going to be the amplitude of 1 or negative 1, I'll show the algebra for this one, but not the rest. So the secant of 2 times 0, which is just the secant of 0, which is 1 over the cosine of 0. Well, unit circle again. Unit circle again. Here's 0. Cosine is 1. So that's 1 over 1, which is 1. So at 0, it's 1. At pi over 2, that means it would be the negative 1. So then we can draw our, quote, wave. X, y, we got x values of negative pi over 4, 0, pi over 4, pi over 2, and 3 pi over 4. So in blue, I'm going to draw the actual cosine wave. Now, the cosine wave, we traditionally start at 0, at x equals 0 with a height of 1. I got to put my heights up here as well. 1, negative 1. So this would be the cosine, and then here, and then here, and then here, and then we'd complete a v. Here would be 2 pi, but because we're drawing a reciprocal function, we know it's a little weirder. That's why we went to the left one. So then we make our nice little wave. It looks more like a sine wave now. That's okay. So that would be, in the blue, that's y equals the cosine of 2x. To draw the reciprocal function, we make asymptotes wherever the original is 0, because we're flipping it. 1 divided by 0 is undefined. And then we draw those little, so in black will be the actual function, y equals secant of 2x. So you have the same heights on the peaks and valleys, and then you just draw little parabola-like shapes inside the asymptotes from there, going up and down appropriately. The bottom one should look a little more like the top one. I just ran out of room. I can't draw through this little section right here because Word is not perfect. That would be Word perfect. Sorry, cheesy joke that probably most people don't even get because who uses Word perfect anymore? All right. One more for the road. For the section. Example 3, graph, we're going to do y equals 2 cosecant of x. So when we're drawing a cosecant, that means we need to flip a sine graph. Now, sine didn't have the weird issue of having to move it a little left. Now, the cool thing is, if you remember what these images are supposed to look like, if you tried to do this previous one from 0 up to pi, so you wouldn't have drawn this segment, and instead you would have finished the wave here, which meant you would have had your actual secant function look like that. When you drew one waveform that went like this, and then this, and then this, having those 3 different looking sections, that's where you should go, wait a minute, that doesn't look like just parabolas being separated by asymptotes. It looks like I've got several different ones separated by asymptotes. So you go, oh wait, no, Mr. Beckner said that's when you gotta shift it left. So all right, from 0, let me just subtract the pi over 4 and then draw the parabola like that. That's a good way to correct that. Okay. All right, so the amplitude A, well, A, not the amplitude yet, is 2. The B is 1 and the C is 0. I don't like doing these with shifts, honestly, for y'all as intro examples. Makes things way worse. So the amplitude in quotes is 2. The period, this is not a tangent or cotangent, so it's 2 pi over B. So 2 pi over 1 is 2 pi. There is no shift. And then the thing that we have to add over and over is the period divided by 4. 2 pi divided by 4 is pi over 2. All right, so the first x value. Now I know that this one, since we literally just did a secant and it had that weird, you got to move left issue. The other one doesn't, cosecant doesn't. We will be able to start at 0 and go all the way up to 2 pi. So the first x value is 0. The second, we take that one and we add pi over 2, which is pi over 2. To get the third, we take that pi over 2 and we add pi over 2 again. We just keep adding pi over 2. Pi over 2 plus pi over 2 is pi. It's 2 pi over 2, which is pi. I'm not going to show that reduction. The fourth one, we take that pi and we add pi over 2. And I skipped showing the reduction for a reason because I know you might do it. But then that means here you'll have to get an LCD. If I had showed it before reduction, I could at least borrow the information. But I did say it at least. Pi is the same as 2 pi over 2. Then when you're adding your pi over 2, you get 3 pi over 2. These are really familiar sounding numbers. And then finally the fifth one, the fifth x value, we take the 3 pi over 2, we add the adding value of pi over 2, which will give us 4 pi over 2, which is 2 pi. These are actually the 5 basic x values when we just do a standard graph, and that's because the b was a 1. When the b is 1 and there's no shift, these x values always end up being quadrantals. The amplitude being 2 will have an effect though. So what's our table of values looking like so far? X, Y. The first one we got 0, then the second one's pi over 2, then pi is our third. 3 pi over 2 is our fourth, and then 2 pi is our fifth. Well, we know the first, third, and fifth are going to be the undefineds. If you don't trust me, go ahead and draw up what we were doing a cosecant, right? Yeah, cosecant, so we're going to drop the sine wave. And with these x values of pi over 4, pi over 2, excuse me, pi, 3 pi over 2, and 2 pi, we know that the cosine was going to look, excuse me, sine, 1, 2, 1, 2. We know that the cosine graph, I keep saying that. We know that the sine graph was going to have these as their points. Those are the ones you better know inside and out. So we're supposed to graph a cosecant, which means we flip the sine graph. So what this is y equals 2 sine of x, not just sine, 2 sine of x, which is why these points are at 2 and negative 2. And then you get your nice, pretty sine wave with heights of 2 and negative 2 for the peaks and valleys. But then what we do is we draw asymptotes wherever this was 0, which is right in the center of our single wave, and then on the ends. And then we draw little quadratics stemming from those. So that's what the graph should be. So we know this is undefined, undefined, undefined. The first one ends up being the original amplitude. I will show the work for that. That's y equals 2 cosecant of pi over 2, which is 2 over the sine of pi over 2. Sine of pi over 2 is 1, so that's 2 over 1, which is 2. You can look at the unit circle and confirm that at 90 degrees, the y value is positive 1. And that makes this one negative 2. And there we go. There's our graph. So in black, is y equals 2 cosecant of x. So these aren't terrible when you have multiple choices you're looking at and you know the idea of how this is done, but it is a much more convoluted problem than just doing a sine or cosine graph because, well, you got to do a sine or a cosine graph just to start the thing and then know how these things are growing from there. And we did lightly describe the reasons they look like this because as the sine number is getting smaller, the reciprocal function should be getting bigger. The closer you get to 0, in the one function, the reciprocal is getting closer to infinity. So it starts growing really, really, really fast. Okay. So that will close out 5.6. Inverse trig functions. This to this, enter, left, lots of enters, lots of space. There we go. Inverse trig functions. So back in Math 161, back in pre-calculus, 163, wherever you had it, whatever number it was called, you were supposed to study inverse functions in that class. And inverse functions, I always liken to Jeopardy. It's where you have the answer and you're wondering what the question was. That's the concept of inverse trig function, of just inverse functions in general. You have the answer and you're wondering what the question is. And in mathematics, this is very often a much more complicated type of problem. In fact, you've all done an inverse problem before you even got to pre-calculus, square roots. The square root of 100 is 10 because 10 times 10 is 100. And it's like you got the answer to something being squared equals 100. And you're trying to figure out what was the question. What squared equals 100? So the square root is our first inverse problem. And in math, this inverse problem can get very, 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 very crazy, but we're not really there yet. So the idea of functions being invertible, first of all, is that it had to pass the horizontal line test. So this is Math 161 or Pre-Calc 1, whatever you want to call it, to have an inverse function. The original function must pass the horizontal line test. And you might be thinking, Mr. Beckner, don't you mean the vertical line test? No, I don't. The vertical line test is to tell if something's a function, which if I'm saying it's originally a function and we're trying to find its inverse, it passes the vertical line test. The reason the inverse idea has a horizontal line test is because what you do to get an inverse function is you change x and y coordinates completely. Left becomes down, right becomes up. So when you take a function and you do this, when your left and right become up and down and vice versa, now in order for that thing to pass a vertical line test, before you changed from one thing to another, those would have been horizontal lines because everything we called left and right before is now up and down, and everything that we called up and down before is now left and right. So that's why this is a horizontal line test. A horizontal line test on a regular function shows that if you do flip everything around, that it would still be a function because then it would pass the vertical line test. All right, so horizontal line test means you can draw a line anywhere and it goes to the function only once at most. Make sure I want to pull that whole thing. Once at most. So 0 is okay, once is okay, but not 2. Due to this, we're going to say, see below, y equals sine of x, stop uppercasing things, must be restricted to a domain of d equals, and then between brackets, there we go. Maybe a little more space than that probably, there we go, is going to be negative pi over 2 pi over 2 in order to be invertible. We have to restrict the domain of a sine function to negative pi over 2 and pi over 2. So the furthest left we're going to go is negative pi over 2. The furthest right we're going to go is pi over 2. You might be thinking, Mr. Beckner, that seems weird. We're going with the idea that sines, when we graph one wave, we go from 0 to 2 pi. Yes, when we're graphing waves, when we're graphing a sine, you go from 0 to 2 pi if there's no a, b, or c written. When we're talking about these inverse functions, this is the window we would need to be thinking about. So here's why. And I'm actually going to do this on like a whole page lower. I want to leave some space here. how much space do I need? That'd be fine up to about there. I think this will do it. So the reasoning below. Here's the graph of y equals sine of x. Now this graph goes forever and ever and ever and ever and ever in each direction. Starts at 0, goes up to a height of 1, comes back down a height of -1, then back up, etc., 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 etc. It goes on forever and ever and ever. So this graph right here, if I drew a horizontal line way up here, it's fine. That doesn't even touch it at all. But if you draw it anywhere in this window, look at how many times 1, 2, 3, 4, 5, 6, and that's only what I've illustrated. This thing goes on forever and ever to the right, so this wave crosses that horizontal line infinitely many times. This is not invertible. So we restrict it. And you're going to see me just try and restrict this in a couple different ways. The first thing some people think is, well, let's just go from 0 to 2 pi. You just go from 0 to 2 pi. Well, look, you still fail once, twice, even down here. Once, twice. So that wouldn't work. So you can't just go from 0 to 2 pi. So the first instinct a lot of students have is, well, let's just half it. Let's, instead of going from 0 to 2 pi, let's go from 0 to pi. And if I go from 0 to pi, that's not it. It looks like this. And this, guess what, still fails. It's not invertible. So in fact, that right side of the wave, the furthest that you can go up to is pi over 2. Because the second you go past pi over 2, if I go just a little bit lower, now I'm going to fail the horizontal line test. So that's the right-sided restriction. And you go, okay, well, let's just go from 0 to pi over 2. No. Remember, we wanted to try and have as much as possible for our domain of a restricted function. And we did this for x squared back in Math 161, if you had me. Where we only had to cut off the left half of it, but now we got to cut off a lot. So we got from 0 to 2 pi. Well, maybe we could go left. Well, we know that the left side of the wave would do this if we kept going, but I've gone too far. That would fail the test. So what I got to do is stop when I hit the lowest point. I got to stop right here, which would be at, guess what, negative pi over 2. That right side looks just a little ugly. Just make it a little prettier. There we go. So in terms of an invertible function for sine, just for sine, that's all we can look at. That is going from negative pi over 2 to pi over 2. This is invertible because any horizontal line you draw will only touch it one time. So that's why we did this. Y equals sine of x must be restricted to a domain of negative pi over 2 to pi over 2, and those are brackets, which means they are included. Okay, so back up top. So we have notation, and I'm going to have to write in pen for this, or it's going to take me forever. So y equals sine of x, that's the normal trig function we've been dealing with so far. Y equals, and the way we read this is not sine to the negative first power. This is inverse sine of x. This is what I was saying back in 5.2. There were at least 1 or 2 homework problems where you have to use this in your calculator, but it was just a calculator thing and they taught you how to do it. That's why I didn't approach it yet. I didn't want to talk about inverse trig functions then because I knew we were going to do this grand detailed introduction later. I figured 1 or 2 homework problems, people are just going to dust under the rug for now and not worry about it. All right, so this is read as y equals inverse sine or sine inverse of x. So when you do the inverse of a function, everything swaps. X's and Y's swap, which means inputs and outputs swap, which means domains and ranges swap. So this, instead of having that domain from before, we'll have a range, which is the Y values of R equals negative pi over 2 comma pi over 2. The domain of a regular function is the range of an inverse function. The domain of an inverse function is the range of a regular function. They swap. X's of one are the Y's of the other. Y's of one are the X's of the other. Now, before, I didn't write this, but the range for sine of X was from 1 to 1. Why? Because these heights are 1, these heights are negative 1. Even with the restrictions, that highest high is 1 and the lowest low is negative 1. So the range of sine of X between negative 1 and 1 would be the domain of the inverse function. So that's the sine function. In its inverse. So now let's do the cosine. So y equals cosine of x must be restricted domain of d equals, and some brackets, some space, close them. And this is going to turn out to be 0 to pi. Of course, it's not the same as sine. Why would it be, right? They always have these subtle differences, and you're not going to figure out and remember these subtle differences without practicing this stuff over and over, without writing notes, without taking notes and reading them over and over, going back to them, highlighting stuff, whatever. So cosine must be restricted to a domain of 0 to pi. Now, I explained why sine had to be restricted, so of course I'm going to do the same for this. So I'm also going to say due to this, which we'll say see below. So we're going to prove that we need to restrict the cosine graph to 0 to pi. So for y equals cosine of x, which originally, when you go forever left and right, heights of 1 and negative 1, we start at 1, and then we're going to go down and then back up and then back down, back up, forever and ever. And the same thing if we were going left, and they'd be a little prettier than what I have, but you get the idea. Clearly, this fails horizontal line test miserably, the same as the sine did without restrictions. So we got to cut this thing down. And the first attempt you might have is, well, let's just go from 0 to 2 pi. So if you go from 0 to 2 pi, we know it starts at a height of 1, goes down, and then back up to a height of 1, eventually like that. But clearly, fails. That wasn't a horizontal line, but it fails. It's a little slanted. So 0 to 2 pi is too much. So a lot of times we'll just cut it in half. And then if we think we need to go to the negatives, we will. So instead of going from 0 to 2 pi, what if you chopped off everything over here? Would that be good enough? Well, I don't see anything that looks like it would fail the horizontal line test, so let's try that. Let's just go from 0 to pi. All right, so that's now going to be a pi over here. You can put pi over 2 up here if you like. So cosine starts at a height of 1 here. And by pi over 2, it's going to be here. By pi, it's down at negative 1. But it's not a straight line. It bends. It waves. That's not the best wave I've ever drawn, is it? A little better than that. There we go. There we go. Much better. This appears to pass the horizontal line test. Passes, passes, passes. So we're good. Now, this is good, so 0 to pi works, but you might, it's always worth trying going to left a little. So pi is as far right as we can go, because if I went just a little further right, it starts bending back up, and that's where we start failing the horizontal line test. So you might think, all right, well, last time we were able to go left some. Once we chopped this down to pi over 2, we said, well, what if we can go left? And we were able to. But if we start going left from here, we're doing that, and again, we'd be failing the horizontal line test. So this is actually as much as you can restrict it and remain invertible. How are we on time? 30 minutes. So, same idea. Because the cosine is bound with a range of -1 to 1, that means the inverse cosine would have a domain of -1 to 1. And we've already established that since the domain of cosine is from 0 to pi, then it's the range of the inverse function would be that. So y equals, oops, holding my pen upside down, that doesn't help. Y equals cosine inverse of x has a range r equals 0 to pi. And again, that is because the domain of cosine is 0 to pi. And the inverse function has a domain of what the regular function had for range, which is literally the same as the sine, -1 to 1. So the domains of the inverse functions are these values because the regular graphs were stuck between heights of 1 and -1 when we didn't throw amplitude numbers in there. If I threw a 2 or 3 anywhere in here, that would change things in here. All right, something that I'm not really going to I don't want to say this, to really use moving forward. But here was the graph of sine to make it invertible. Here was the graph of cosine to make it invertible. Let's invert those graphs. So here we're going to do the graphs of the inverse functions, inverse sine and inverse cosine only. So all we do is, remember, we swap coordinates. That's all we're doing. So this point right here, which was -pi/2, -1, would now be -1, -pi/2. This point right here that would have been pi/2, 1 is now going to be 1, pi/2. That's the idea. This point here was the origin, so it's going to be the origin when you invert it. So again, taking that graph, can I do this? Yeah, it's going to be weird. What happens if I copy, paste? Oh no, that looks awful. We're just going to leave it there. Okay, I'm going to pull back some. All right, so first we're going to do is the y equals inverse sine of x. Again, it's just taking this graph right here and swapping all x and y coordinates. So the values going from -pi/2 to pi/2 on the x-axis will now be on the y-axis. I'm going to scroll back just a little more. So now we'll have -pi/2 on the y and +pi/2 on the y. And then those heights of 1 and -1 that were on the x-axis, I'm sorry, that were on the y-axis originally, will now be on the x-axis. Then we just plot the points. So this was -pi/2, -1. So now it's -1, -pi/2. Then we had the point at the origin, which is pretty clear to see. And then pi/2, 1 is now 1, pi/2. Now, I'm not going to go in and do all the middle details because this is not something we're going to focus on throughout the rest of the course. But when you bend this way for the regular function, what that means is you're going to bend this way for the inverse function. It's just the way things work. So it actually kind of looks like a cubic here. So remember, the domain is the x values. The range is the y value. So it depends on, are you talking about the regular function or the inverse function? But when I say the word domain, we're talking about x values. When I say the word range, we're talking about y values. But just understand that when you talk about the domain and the range of the regular function, they flip-flop in the inverse function. So that's our inverse sine graph. Now, here's the thing. This does not extend. This is the whole thing. This is the entire graph. It's not like sine and cosine where those waves keep going on and on and on forever and ever. Because we had to restrict the sine graph to be something so small in order for it to be invertible, that means this has to be a relatively small graph as well. If you restrict the regular function severely, then the inverse trig function is not going to take up a lot of space either. Now, what's interesting is negative pi over 2 to pi over 2, this is between negative 90 and positive 90 degrees. So we can almost stay inside of one quadrant, but really that's in quadrants 1 and 4. So this is in quadrant 1 and 4. When you're thinking about your unit circle. And that idea is going to be extremely important because what we're about to do for the inverse cosine, you can probably guess, it ain't the same. So this time we're going to take the cosine graph, which had x values going between 0 and pi, so that's now our y values. Our y values are going to be going between 0 and pi. So something like this, x, y. So let's have pi up here, maybe pi over 2 here. Split it a little more evenly though. There we go. And then 0. So again, those x values become the y values, and the y values become the x values of negative 1 and 1. All right, so we had the point at 0, comma positive 1. So 0, comma 1 is over here. Then we had the point, and 1, comma 0 now, that is to say, 0, comma 1 becomes 1, comma 0. This was pi over 2, comma 0. You flip the order, so it's now 0, comma pi over 2, which is here. This was pi negative 1, so now it's negative 1 pi. And again, because of the bending this way, the inverse function would bend in a different way. So it ends up looking like this at the end of the day. And again, it does not extend. Here's what would happen if it extended. On the sine wave, basically, it's just instead of drawing your waves like this, when you invert the function, your waves get drawn like this. So when you invert a wave, that's what happens. But it's not a function, which is why you had to cut so much of it off. So if you kept going, that inverse sine wave ends up looking like, without getting wider, poor artistic ability on a blind tablet. And then it would do the same thing below. It would keep waving around. We can't do that because then it wouldn't be a function. The same thing happens with this cosine wave. It would come back down to the 1 and then back up to the, or back to the left of the negative 1, right to the positive 1. It would keep doing that same idea, but again, fails being a function miserably, and we only deal with functions in trig. So this, you're going from 0 to pi, which means we're in quadrant, let's go back to blue, 1 and 2 in your unit circle. Again, the fact that sine inverse goes with pairs with quadrant 1 and 4, and cosine inverse pairs with quadrant 1 and 2, that is going to be a major, major, major issue moving forward. This is an issue that a lot of people mess up the first dozen times they do it, and then the second dozen they start getting used to it and getting them right. When is this going to be an issue? When negatives are thrown around. It's always the negatives that mess us up, right? Oh, sine of pi over 3, I know how to do that. Just use that little right triangle, the 1, 2 square root of 3 triangle. What if I ask for sine of, you know, some other value like 5 pi over 3 when we're another quadrant, and it's basically the same thing except it might be negative. It's that same idea here, except it's not the whole. There's two answers. It's only one, because these aren't going to be valid in all four quadrants, only two of them. So while in the past we might have been saying, all right, find all x where sine x equals square root of 3 over 2, that's going to be different than how I'm going to ask it today. And with the very first example, I'll show you the difference there. So am I going to ask you for these graphs repeated throughout this course? No, that's not what I'm going to ask you about. I'm going to be giving you examples like find sine inverse of square root of 3 over 2, or find cosine inverse of square root of 2 over 2, or find sine inverse of 0, or cosine inverse of 0, or sine inverse of 1, anything like that. So I'm basically giving you the ratio of opposite, adjacent, and hypotenuse inside of that inverse trig function, and your answer is supposed to be an angle. We've answered questions like that, but it wasn't using the inverse notation, which is why it was different. When we use this notation, we're restricting ourselves to half a circle by nature. All right, so enough blah, 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 right? Let's get down to it. Let's zoom back in. Example 1, evaluate that A. Let's go back to black. We're going to have the inverse sine of the square root of 2 over 2. So this is the question. This by itself is the question. This right here are your opposites, adjacents, and hypotenuses, hypotenuse, whatever would be respective of this trig function. So sine is always opposite over hypotenuse. So I'm saying that we could form a little right triangle where this would be the opposite and this would be the hypotenuse. Except it's going to be a little funky and it would be harder to find the angle because of this weirdness. So that's where I say, oh, it's actually a really good idea if you remember that square root of 2 over 2 is 1 over square root of 2. But here's what we're doing. So blue, this is not the problem anymore. This is what we're doing. We're trying to find an angle. Our goal is to find an angle such that the sine of that angle is equal to square root of 2 over 2. But restricted because the problem had an inverse trig function. So in like the second or third section of this course, what I have just circled in blue, I gave you that as a problem. I said, I would say find theta such that blah, blah, blah. And I would also say that theta was between 0 and 2 pi, no or equals there. And you would get two answers. Again, if just this blue circle thing was the problem, there would have been two answers because we could have talked about the full circle, but it's not the case. Because we're talking about an inverse trig function, these inverse trig functions have restrictions. Specifically sine, you're stuck in quadrants 1 and 4. Cosine, you're stuck in quadrants 1 and 2. There's an even bigger issue here. It's not that you're just stuck between quadrant 1 and 4, but if you wanted to answer, say, 330 degrees, that's wrong. Even if technically speaking, 330 degrees is coterminal to the correct answer. The correct answer would be negative 30 degrees because this thing does not go between 0 to 2 pi, and 330 would be up there near 2 pi. It goes from negative 90 to positive 90. So you would have to turn that 330 degrees into negative 30 by doing coterminal angles. You've got to understand how that works. Which the cool thing with negative angles and sines is you just make it negative of the reference angle. It's pretty easy, in fact, as we'll see. Okay, so we're trying to find an angle such that the sine of that angle is square root of 2 over 2. This is the same as trying to find the sine of an angle that's 1 over square root of 2. So that tells us to use the 1, 1 square root of 2 triangle, which is right here, 1, 1 square root of 2. Sine would be 1 over square root of 2, opposite over hypotenuse. So the angle is 45 degrees, but we're going to keep everything in radians for this. It's another issue. With inverse trig functions, these need to be in radians. You are not supposed to use degrees for inverse trig functions. I do believe my math lab will mark that wrong. So theta would be pi over 4. And because this was positive, that's the answer. If you don't believe this, the sine of pi over 4 is square root of 2 over 2. So the inverse sine of square root of 2 over 2 is equal to pi over 4. That's what we're saying. We are saying that the inverse sine of square root of 2 over 2 is equal to pi over 4. We're finding angles when the question is an inverse trig function. We're finding ratios of opposites, adjacents, and hypotenuses when the question is a sine or cosine problem. So in red, so like in, I think this was 5.2, 5.3, the question would have just been this. It would have been find theta, so the sine of theta is equal to square root of 2 over 2. Sorry, find all theta. Find all theta, where 0 is less than or equal to theta is less than 2 pi. So full circle, well, we'd say, oh, well, we need a reference triangle for this. So a reference triangle, and again, that's 1 over square root of 2. So you put your 1 here, you put your square root of 2 here. This is your reference triangle. That makes this also a 1, and that makes the theta prime 45 degrees. But then you say sine is positive in quadrants 1 and 2. Because sine is the y value, you go up in quadrant 1 and 2. So the first solution is the reference angle of 45 degrees, which is pi over 4. But theta 2 should be in quadrant 2. So you put your reference angle of pi over 4 there. That's in quadrant 3, excuse me. 2. So this right here is your pi over 4. This right here would be your second actual angle. And when you do pi minus pi over 4, it turns out that theta 2 is 3 pi over 4. So pi over 4 and 3 pi over 4 were the solutions. But with this inverse trig, because of the restrictions, it's only one solution. Inverse sine is not valid in quadrant 2, so in the actual problem, because we worded it this way, we can't involve quadrant 2. That's why we have to toss it out in this problem we just did. That is a big distinction. That is a distinction that people mess up. I'll see students in the red ink, if I gave them the red ink problem on a test, which I certainly can, they only give me one of the answers. And then I'll give the inverse trig problem and they give me 2 answers. You've got to keep things organized. You've got to know when to restrict, when not to restrict, when to use the full circle, when not to. And when you have restrictions, what are the restrictions? Where are you stuck to? All right. B, black, not blue. We're going to do inverse sine of -1. Okay, so the idea here is the problem that you're really doing is you're finding, again, the black ink is the whole problem, but then what you're thinking about is finding an angle such that, or so, the sine of that angle is equal to -1, but restricted to what? Quadrants 1 and 4. So again, now in the blue ink, this is more like something we had in 5.2, 5.3, but I'm not going to consider all 4 quadrants. I'm a lot less likely to get 2 answers. I'm much more likely to only get 1 answer. In fact, with inverse trig functions, it's always just 1 answer. All right, so sine being 1 or -1 only happens at the quadrantals, so we need to go to our unit circle. So we go to our unit circle, and we're trying to say, where's the sine, which is the y-coordinate, -1? Well, here's a -1, but it's the x-coordinate. Here's the -1 is the y-coordinate. So the answer in, that was weird. The answer in degrees is 270. In radians, that would be 3 pi over 2. So 270 degrees is the same as 3 pi over 2. And that does put us in between quadrants 1 and 4, so we're okay. So here's what somebody would do. They'll say, okay, so it's unit circle, it's quadrantal, it's at 270 degrees, which is 3 pi over 2. But if you put, and while those are arguably correct based on the periodicity of trig functions, if you put this in my math lab, if that was your answer, guess what it does? It marks it wrong. And it is wrong. It is coterminal to the actual answer, but because we use this inverse trig notation, the restrictions are very specific. Not only are we restricted to quadrants 1 and 4, the way we label values in quadrant 4 is specific in that we don't go from 3 pi over 2 up to 2 pi. We have to be using things between 0 and -pi over 2. Those are the values we would be saying. So 3 pi over 2 is the same thing as -pi over 2, and this is how you have to answer it for an inverse trig function, because 3 pi over 2 is outside of the range. -pi over 2, the coterminal version of that, just rotating clockwise instead of counterclockwise, is in the appropriate range. So that's the answer. That's the only way to answer it. So theta is -pi over 2. And I know it seems ridiculous that, well, 3 pi over 2 is the same answer. It's coterminal, and we've never had a problem with this before. And you are right that we hadn't had that problem before. But in life, very often, we have to restrict ourselves to a very small set of rules, parameters, values, whatever. And there's a lot of things we do with inverse trig functions, so this is important. In fact, your calculator is very likely to mess up inverse trig functions. About half the time, if you're not paying attention to your quadrants, it'll say, oh, it's this thing, because it won't worry about the restrictions and everything, and then it's actually wrong because it might have something to do with an issue like this, or maybe you put an angle that you think is in quadrant 2 and really it's supposed to be in 4, or vice versa. All right, let's do another one. We're going to do a bunch of these, clearly not all of them today, since we only have about 8 minutes left. All right, inverse sine of the square root of 3 over 2. Now again, we did problems just like this in a simpler way before, back in like the second and third section of this chapter. I would have said, though, find all theta such that sine of theta equals square root of 3 over 2, and the angles between 0 and 2 pi. And I even could have done restrictions there to kind of, get that idea going. I did that once or twice. So when you see this question, this is what you're thinking about. You're trying to find an angle such that, or so that, the sine of that angle is equal to square root of 3 over 2, but restricted to, and instead of saying quadrant 1 and 4, I'm going to be even more specific now, -pi over 2 to pi over 2. That's still saying quadrant 1 and 4, but I'm being very specific with the language of how I have to write any angles from quadrant 4. I can't call them 5 pi over 3. I'd have to call it -pi over 3. I can't call it 11 pi over 6. I'd have to call it -pi over 6. Well, sine of theta equals square root of, sine of theta equals square root of 3 over 2. Well, that's our 30, 60, 90 triangle with opposite of square root of 3 and a hypotenuse of 2. So let's go over to our unit circle. Not unit circle, excuse me, the special triangles. 30, 60, 90, 1, 2, square root of 3. So we're just trying to figure out, is it the 30 or the 60 degrees? Well, we're doing sine, so the opposite's supposed to be the square root of 3, so that should be the opposite. This should be the hypotenuse, which says that our angle is the 60-degree angle but we're going to use the radian version for inverse trig functions. Again, I believe my math lab should be marking those wrong if you put it in degrees. So our angle is the 60 degrees, which is pi over 3. Now, since this is positive, this should be positive. If that had been negative, spoilers, this would have been negative. I will not be surprised if Word crashes. It keeps giving me that blank, like, refresh thing. And I know if I hit save, it will, so I'm not going to hit save. So the angle is pi over 3. That's inside the appropriate window. And that's it. And again, that was based on the right triangles. D. Do we have time for one more? Yes, we do. And before I do D, I wanted to make that memo. I just said that, but I want to type it out too. So special note, if the inside of inverse sine is negative, that just means the angle is negative. It's just the reference angle, but negative, because that's how going from quadrant 1 to quadrant 4 works. You're just spinning in the opposite direction. So I will, in literally 5 seconds, give you a D, a fake D, but an alternate version to C. What I'm saying here is, if this problem had been this, if C had been this way, if I had asked for the inverse sine of negative square root of 3 over 2, then this answer would have been negative pi over 3. That's for inverse sines only. I'll give you a special case of that rule for inverse cosines, not today, but it does give you kind of an easy way to do things. Actually, on that note, let's go ahead and call it. No, we are going to do D. I'm sorry, I have enough time. I was looking at E, and I was thinking I didn't have enough time. But I should be looking at D, shouldn't I? Inverse sine of negative 1/2. So what we're doing is we're trying to find some angle so that the sine of that angle is equal to negative 1/2. These are the same problems, just without restrictions, but we know that this is restricted to the negative pi over 2 to pi over 2. And I'm going to write it in interval notation this time. Well, we can just delete the negative and call it a reference angle. So that means the theta prime would go here. It would have an opposite of 1, a hypotenuse of 2. That's the 1, 2 square root of 3 triangle. And that says that theta prime, that's opposite the 1, is the 30 degrees, which is pi over 6. But this is supposed to be negative. Sine's negative in quadrants 3 and 4. But we don't include quadrant 3 because inverse sine is restricted out of quadrant 3. We only include quadrant 4. So we put the theta prime in quadrant 4, but using all that stuff, not calling it 11 pi over 6, that would be outside of the restrictions. We have to call it negative pi over 6. So I verbalized all the different details there, but also, I mean, if this was a negative, this is a negative. It's easy as it gets with sine, and it's inverse. All right, so we're going to stop there. We will do 3 or 4 more, 2 to 4 more next time. We'll also introduce the inverse tangent. We'll also introduce a much more complicated type of problem involving this. And then we'll show what the simple homework problems from 5.2 and 5.3 were, word problems where you're trying to find an angle given like an opposite and a hypotenuse or an opposite and adjacent. And it's just as easy as using a calculator. So we'll share that next time. But for now, we're pausing on this section. We'll come back to 5.7 next time. We did finish 5.6 today, though. So email me with any questions. I'll have this video posted in an hour or two. Take care. Have a good day. We'll see you Wednesday.